Johnny here, and in this video I'm going to graph the tangent function and its reciprocal, the cotangent function. I'm assuming you have already watched my sine and cosecant video where I kind of go through the motions slowly. I'm going to go a little bit faster here. So I'm going to start off with tangent. Now the tangent values, a lot of students don't have memorized, so get out a unit circle or a make an XY chart if you need to. But I know tangent is very pretty at the pi's, the pi halves, and the pi fourths. I'm going to label my input axis, my theta axis, or my x-axis with the angles. And I'm still practicing this. So I'm skipping dash, 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 skip, dash, where this tally mark is pi halves. That's because every tally mark has been 1 pi 12ths, or 15 degrees. So 15, 30, 45, 60, 75, 90. 90 degrees is equivalent to pi halves radians. Half of that is pi fourths, or 45 degrees. Now, if I label one square to be 15 degrees, then two squares must be 30 degrees. Okay. With that in mind, I'm going to continue. Skip, dash, 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 skip, dash. There's 1 pi. Skip, dash, 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 skip, dash. 3 pi halves. Skip, dash, 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 skip, dash. 2 pi. I have now mapped the x-axis out one full revolution around the unit circle. I'm going to go ahead and label all of the fourths. So 1 pi fourth, 2 pi fourth, 3 pi fourths, 4 pi fourths, 5 pi fourths, 6, 7 pi fourths, and then of course 8 pi fourths would reduce to 2 pi. Similar to my sine graph, I'm going to let 4 squares be 1 y unit. So 8 then must be 2. I know tangent has some negative outputs, so I'm going to label -1 and -2. Now I'm just going to go along the unit circle and list some points. Tangent of 0 is 0. Tangent of pi fourths, we are in quadrant 1, where that is a positive 1. Tangent of pi halves, well, that's undefined. So guess what's happening at pi halves? An asymptote. Tangent is undefined at pi halves. That's because we're taking 1 and trying to divide by 0. By the definition, the y value of 1 over the x value of 0. Doesn't quite work out, so it's undefined on the unit circle. Graphically, that means we've got an asymptote at x equals pi halves. Continuing, 3 pi fourths, we're now into quadrant 2, where tangent becomes negative, and 3 pi fourths is pretty, so tangent is a -1. Tangent of pi is 0. 5 pi fourths is in quadrant 3, where tangent is positive. It's a lovely 1 again. 3 pi halves, or 270 degrees, is straight down. The y value is -1 divided by the x value 0. Again, tangent is undefined at 3 pi halves. That's going to create an asymptote on the graph itself. Tangent of 7 pi fourths. We're now in quadrant 4, where tangent is negative. 2 pi, we're back to the coterminal angle 0, where tangent is 0. I have to admit, not very many points, but I do know the shape. I'm bounded by these asymptotes. As I move left to right, it's clear that I'm increasing. There's probably some curve to this. If you would like to get a better estimation about what this graph looks like, well, we can go in and add in at least quadrant 1, pi 6 and pi thirds. Make a little XY table. If I plug in pi 6 into the tangent function, tangent of pi 6 is root 3 over 3. That's the exact value. But if I want a decimal approximation to help me, visualize where that point actually is, I can estimate. Root 3 is bigger than 1, less than 2. It's really close to 1.7, but I'm about to divide that number by 3. So 17 divided by 3 does not sound fun, but 18 does. So like before, I grossly rounded root 3 up to 1.8. I'm going to do that again, because that is nicely divisible by 3 to be about 0.6, knowing this is an upper estimate. So pi 6, if 2 squares is 0.5, then 0.6 is right around here somewhere. Put a little tally mark there. I guess the tally mark would work. I'm going to call that root 3 divided by 3. Okay, pi thirds. Tangent of pi thirds, well, it's just a reciprocal. It's going to be a root 3. Oh, so it really is really close to 1.8. More like 1.7, but I'm rounding up to 1.8. So at about pi thirds, I need to go up to about 1.8-ish. I'm labeling the y-axis with an exact value, not the decimal approximation. And this confirms my suspicion that as I move to the right, I'm going to increase, and notice the jump. I go bam and then bam. So in 2 tally marks, I went 2.5-ish. In another 2 tally marks, I went 1, 2, 3, 4, and some change. So the closer I get to the pi halves, the faster I am increasing. So notice that point didn't quite fit my scale. I'm not even going to try to. I'm just going to make this as curvaceous as possible. If you want that to fit, a nice way is just to make that point big. There we go. So it looks like something similar is going to happen between the 2 asymptotes, where I am curvaceous, and it's almost like I'm going to try and turn around at pi, but I was just kidding. I'm not. I'm going to do something like this. So when we are zoomed in this close, it has that cubic feel to it, but of course it's not, because I'm bounded by these asymptotes. So if I zoomed out just the slightest bit, it would look like 2 straight up lines, 2 vertical lines. But similarly, over here, I'm going to, as I move left, decrease really, really fast. So in black, I have graphed tangent over the interval 0 to 2 pi. What then is my period? What's that horizontal distance that it takes me to begin to repeat myself? So if I start at 0 and I'm increasing, that seems to happen again at pi, where I'm just repeating myself. So cosine, sine, cosecant, secant all had periods of 2 pi. Tangent has a period of 1 pi. Amplitude, a dumb question. There's no maximum value. If I ask you this, you just say it's not applicable. Really only sine and cosine have amplitudes. It's the waves, and you want to know how high is the wave from a zero position. Domain. Well, it does look like I have some problems. Pi halves is a problem. 3 pi halves is a problem. Negative pi halves. 5 pi halves. Negative 3 pi halves. 7 pi halves. I'm going to use set notation here. And I'm going to list a bad one. So I'm going to say all x values seem to be fine, but not pi halves. So the set of all x values such that x cannot be pi halves. And then to that, I'm going to add a distance until the next problem. Looks like a distance of 1 pi. So I say x cannot be pi halves plus every interval of pi after that, like integer. So yeah. X-intercepts. Well, I would say 0, 0, pi, 0, 2 pi, 0. Oh no, this is going to go on forever. Negative pi, 0. No, this is no good. I'm going to come up with a cleverer way to say this. How about the set of all x comma zeros, I guess, such that x is, I don't want to list a good one. 0 would be the smartest route, but I'm going to pick a non-smart route. I'm going to say a good one like pi plus the distance to the next good value, or the next x-intercept, which is 1 pi away. I've already defined k on this sheet of paper, so I don't think I need to do it again. But this is just saying at pi comma 0, at 2 pi comma 0, these integers include negative numbers, negative 1 pi. If k were 0, it would be pi. I'm good there. Range. I seem to have no problem. All real numbers. Y-intercept. Well, tangent of 0, 0, so 0, 0 will be my y-intercept. That coordinate is 0, 0. All right, so tangent shows all of its values much faster than sine and cosine. It only takes me 1 period. And it has this cubic, squished cubic feel to it. Now I think cotangent might be a nice one to graph on the same graph. I'll do that in green. Now, tangent and cotangent, they are reciprocals of each other. And on the unit circle, those values of root 3 and root 3 over 3, those are reciprocals of each other. So these are going to go very nicely. Oh, but straight off the bat, we got a problem. What's the reciprocal of 0, though? Nonsense. It is an undefined asymptote. So tangent of 0 is 0. I take that output 0 and reciprocate it. The reciprocal of 0 is undefined. Cotangent starts off with an asymptote. 1 is easy to reciprocate. What's the reciprocal of positive 1? Positive 1. That point stays there. Now, root 3 over 3 and, oops, God, why didn't anyone raise their hand and tell me that I did this incorrectly? This point at about 1.7, 1.8 is root 3. I don't know why I labeled it root 3 over 3 like this. Let me try that again. These values, root 3 over 3 and root 3, they are reciprocals of each other. You should have maybe figured that out by now when you were playing around with that unit circle. But if not, play with it now and see. Root 3, if I reciprocate it, I get 1 over root 3, which needs to be rationalized. So I multiply by root 3 over root 3, giving me 3 root 3 over 3. Oh, but then I have a 3 up top and a 3 down below. Those 3's reduced, leaving me with root 3. Oh, yeah. All right. These are root 3 over 3. These are the reciprocals of each other. So when I reciprocate root 3 over 3, I'm going to get out root 3. When I reciprocate root 3, I'm going to get out root 3 over 3. I think I've got it. This makes sense to me. Instead of rising to the right, I'm falling to the right. Well, what's cotangent of pi halves? Well, up top, tangent is undefined because it was defined as the y value 1 over the x value 0. So tangent was undefined. But if I take that tangent value and reciprocate it, 0 over 1, now all of a sudden the division is possible and I get 0. So where tangent is undefined, cotangent is defined to be 0. That's going to happen again at 3 pi halves. These values are 1s, so they're going to stay put, 1s and negative 1s. The 0, though, becomes an asymptote. And I can see that that shape is just going to continue again. And so there's no need to do that. This is a periodic function. Cotangent clearly has a period of 1 pi. If I go any further, I'm just repeating myself. So it's okay to show more than one interval, but I don't need to waste my time. I know what cotangent now looks like. It looks like this. So where tangent is a wannabe cubic smushed between asymptotes, cotangent is a wannabe negative cubic squished between two asymptotes. I'll use this one over here to talk about things like domain. Well, I start off 0 is a problem. Pi is a problem. 2 pi will be a problem. Wherever tangent hit the x-intercept, the x-axis, wherever tangent has x-intercepts, that's going to be a asymptote for cotangent, or it's undefined. All right, let's see if I can do this. The set of all the x values. I think I'm finally going to try to be smart here, such that x cannot be 0 plus pi. Well, that 0 plus pi is ridiculous. So I'm just going to say pi k. If this confuses you, well, don't panic. You can go back to what we were doing, where you can say x cannot be pi plus pi k. I'm just acknowledging that because one of those values is 0, it can be a little bit more elegant. I think this will handle it. And we can test a few integers to find out. If k were 0, 0 times pi is 0. Bam. 0 is a bad number for cotangent. If k is 1 pi, I've got an asymptote. Look at the green graph. K could be 2 pi. Yeah. Any interval of pi seems to be a problem. If you want to put a 0 plus in there, it's still legal. It's still fine. Since we're talking about x values, do I have any x-intercepts? Well, I have one at pi halves, so I'm going to say the set of any, I think in some videos I was just saying the x value, which is fine. I'm going to try to do this as a coordinate though. X-intercepts really are coordinates. So I'm going to say x comma 0 such that, list a good one. So I'm listing a good x-intercept, pi halves plus pi k comma 0. Oh my gosh, I ran out of room. It looks hideous. Let me try that again. I don't want you to stress too much about this notation, but I am trying to get the point across that I can't just sit down and list every x-intercept. So I'm trying to come up with a clever way to do so. There's not just one fail-safe way to do it, but I think this kind of makes sense. I'm listing, so a set. I'm listing all of the x-intercepts, and every x, well, in such a way that x is defined as pi halves, I'm listing a good one, plus pi k comma 0. I think that makes sense. All right. Range, I seem to have no problem. Negative, I'm looking at the green graph, negative infinity up to positive infinity. You could say negative infinity to positive infinity. I'm going to say all real numbers for shorthand. Y-intercepts. Well, cotangent, the green graph, never touches the y-axis because it's undefined at 0. So I'm going to say that. And I have here graphed both tangent and cotangent over the interval 0 to at least pi. So in green, I can see the full cotangent unbroken. Looking at tangent from 0 to pi, it does have a break in the middle of it, which is no big deal, but it does. If I were to change the window or the interval from pi halves to 3 pi halves, then tangent is unbroken. Looks nice and pretty. I can see all of the outputs of tangent in one nice graph, unbroken. But the cotangent is now broken. All right. Practice. Practice. Go graph these. And once you've done it, do it again. Practice. Repetition. Repetition. Practice. Repetition. Practice. Go graph cotangent. Graph tangent and then cotangent. Graph cotangent and then tangent. Graph. Graph.